Hi everybody, this is Shujat. In the first video, I've already explained you about what one-way MANOVA is, and I gave you a brief summary of the various assumptions of one-way MANOVA. In this video, I'm going to demonstrate how we can perform these assumptions or how we can test these assumptions with the help of SPSS. I have the data on the three dependent variables, that is positive mood state, negative mood state, and level of perceived stress. And the primary research question is that we want to check that whether these three variables differ by male and female or not. So the first assumption I've already discussed in the last video. I start from the second assumption, that is of the normality. So before applying one-way MANOVA, we have to ascertain that data is both univariate, have the univariate normality and the group variate normality. Univariate normality means that each individual series have is normally distributed, and group variate normality is that overall data has normality. So for checking the normality or for ascertaining the normality, we have a couple of tests. There are a lot of tests, but in fact three major things are checked for. There are two things. One is skewness and kurtosis. The value of the skewness and kurtosis, it should float between 1.96 to minus 1.96. And there are other tests. The famous one is the Shapiro-Wilk test, which should be insignificant in order to be data normal, in order for a data to be a normal. So I'm going to apply these tests on the data set which I have with me. The data set has been obtained from the open source one of the website of SPSS survival manual. So okay, again to repeat, we have a three dependent variables: total perceived stress, total negative, and total positive. Total perceived stress, total positive effect, and total negative effect. So this is this variable, and then total negative effect, and this is total positive effect. So we want to check that whether these three variables are normally distributed or not. So for the univariate normality, obviously we have to check the normality of the variable one by one. So what is the procedure for checking the normality? First of all, we go to analyze, then we go to descriptive stats, then from descriptive stats we go to explore. And this is, since I've performed a couple of things before, so that's why they are appearing here. Here in the dependent list, we have to drag, and we have to put our one dependent variable. So in the dependent list, for example, I start from the total positive effect, so I drag it here. In the factor list, this one, in the factor list, we have to drag the variable on the basis of which we are categorizing the variable. So here in our case it's gender or sex, because we are dividing the data into two groups on the basis of gender, so we are dragging here. Now once we drag the variable of factor list here in the factor list box, it means that it's going to divide data into two streams, one for male and one for female, and each stream would be checked for its normality. Right afterward, you just click on stats, and presently there's no need of outlay since I performed a couple of other tests, so that's why it's some of the ticks are appearing. So simply you click on the plot and click here normality plots with the test, and continue, and then it's okay. So these two tables are important, this descriptive table and test of normality. I have already brought these tables here in my slides for explanation. In fact, you see that based on the gender, they have the software has calculated separately the values for the male and for the females both. So here you can just see in the in the box which has been, I have highlighted in red, this circle, skewness is minus 0.758. This is the stats of it, and 0.179 is the standard error. Again, this is the value of the kurtosis, and again in front of that is the value of standard error. So how we can get the value of the skewness, which we have to check for that it's between plus 1.96 and minus 1.96. So simply what we do, we divide the standard error. sorry, we divide the stats with the standard error and we get the corresponding value. For example, here in this case in female I've already done that. I've divided minus 0.887 with 0.153 and the value is 5.797. So stats divided by standard error, we are getting this value. The same you can do for the male, and now we have to check that whether this value floats or it lies between 1.96 and to minus 1.96 or not. So obviously this 5.797 is out of that particular range, and the same is here. So it is showing that the data is not normal. In order to ascertain or to recheck the results or to retest the results, we go to the other test of normality. That's one is this Komogrov, Smirnov and Shapiro-Wilk. They are the two tests. The values of these tests should be insignificant in order to be a data normal. Now in our case you can just see that the values are significant. It's showing that the data is not normal. So both of the tests are this both of this normality test and both here tests are explaining the data is not normal. So once the data is not normal, to make the data normal there are a lot of approaches, but one of the major approaches that if we make data free from the outliers and missing values, so we can convert data into normality. So in order to free our data from the outliers, which is also our second assumption that the data should be free from the outliers, we move forward that how we can check the outliers in the data and how we can make the data free from the outliers. In fact, to check the outliers in the data, we have to run the Mahalanobis distance test, or we have to check in fact the Mahalanobis distance values. Mahalanobis in fact tells us, or it shows the variables which are the outliers. It in fact clearly explains or clearly tells that what are the variables which are the outliers and what are the variables which are not outliers. So let's apply the Mahalanobis test. Procedure is here, but I'm going to apply this procedure for you to understand that how we can find Mahalanobis test. Okay, I go there, analyze. This is a regression, then linear. Mahalanobis test is, since I have already applied, so there the things are here. I just make it as, move it back. Okay, now the thing is that here in the dependent list we have to drag ID of each of the data, right? ID means that each of the data series have been given a certain number. If here you can just see that this is 94253074404. This is the series of the data number, so this is ID. And in the independent box we can even move all the dependent variables together, so wherever there will be outlier it will be exposing the outlier. So simply first I drag here ID, then I drag my dependent variables, total positive, total negative, total perceived stress here, right? So afterward we can, in the stats we just need the estimates. Simply go to the plots. I think in the plot we don't need, we go to the save and we click on Mahalanobis test, which is already clicked, and then we go to continue. Okay, and then you will see that there will be a box. This box would be appearing. So I am just going to bring this box to the slides here. So this box has been exactly, I have just brought already in the slides. So you can just see that here in the Mahalanobis distance a value is appearing which I have highlighted in red, 18.101. This is the highest Mahalanobis value. We can say that this is the computed Mahalanobis test value. Now we have to compare this value with the tabulative value, or the value which has been taken from the table of the Mahalanobis. So this is a Mahalanobis table which I have taken a piece of that table and I have put here, which is showing our critical values against our number of dependent variables. Yeah. So in our case we have 3 dependent variables. Mahalanobis critical value 16.27. If we'll be having 7, for example, dependent variables, the value would be 24.32. So in our case it's a 16.27. So in order a data to be, and in order for data to be free from the outlier, the tabulative value should be greater than the calculated value. Means the value which we are taking from this table, it should be greater than the value which we are getting or which we are computing with the help of the SPSS. It means that tabulative value, or here I have written simply tabulative value, you can write a critical value, it should be greater than the calculated value. In our case it's 16.27, and the value which we have computed is 18.10. It means that it's showing that the critical value is less than the value which we have computed through SPSS. So it is showing that not data is not obviously normal, and data has the outliers. So it means that there are the outliers in the data. There are some of the observations which are beyond trend. There are some of the observations which are against the trend of the data. There are the observations which those observations do not appear to be like the rational observations. So those outliers are irrational kind of observations. We have to identify them and we have to delete those observations. Now second step is how to identify the observations or the data which is outlier, the observation which are outlier. So this test we are going to apply to identify the outliers. I'm going on the SPSS to perform this. Simply I just for you to just have another look, go here on analyze, descriptive stats, and explore. Right here in the dependent list, we have to drag this variable Mahalanobis distance 4. You know that this variable is being created by or being generated by the SPSS. What happens that each time when we want to get the values of the Mahalanobis test, it creates one new variable with the name MAH underscore. The first variable would be MAH underscore 1, then the second would be MAH. So the number of time you run the Mahalanobis test, every time it creates a new variable. So since now just I run the test, so this MAH underscore 4 is the series which is showing our variables, which is showing the variable's distance from its mean, that whether there's outliers or not. So I'm just going to drag this Mahalanobis distance here in the dependent list, and then in this label cases I'm going to drag this ID here. We can go to the stat. I think we just need the outliers. Rest we don't need anything, right? So you just go and click on OK. So we can get this particular box. Sorry, yeah, it's test of normality has appeared because already I clicked some. So we need this particular box, the box of extreme values. So I transfer this box of extreme value here in the PowerPoint slides. How you'll get to know that this value is a kind of extreme value. We have the benchmark value which we have already calculated, that is 18.101. So all of the values which are greater than 18.101, sorry, we have in fact the benchmark value, this is 18.101, but our benchmark is 16.27. sorry. So all of the values which are greater than 16.27 means the critical value, those are the outliers. So in our case this 18.10 is greater than 16.27 values. So observation number is 415 ID. So it means that this 415 is our outlier. This particular ID is outlier. So simply we go here and just I delete this observation. Even so this observation has been deleted. Now again I can run the same test and I would find that the data has been free from the outliers because we have already deleted the data from the outliers. So in this way we can remove the outliers from the data, right? So if you can run again this test and you will be finding that there will be no outlier in the data, right? Then the third assumption of MANOVA is linearity. Linearity means that the variables, the dependent variables should have a linear relationship with each other. In other words, there should be a moderate correlation among the dependent variables. So if we have the three dependent variables, each of the dependent variable have at least a kind of a moderate correlation, and the relationship should be a straight line. Linear means a straight line. It shouldn't be ups and down. Non-linear, it shouldn't be a curvy relationship. So in order to find the linearity of the data, we simply plot the data, we plot the observations against each other, and we check that whether it makes a straight line or not, right? So as I told you previously, that once we were checking the normality, that if we have the data grouped into male and female, so for both groups, for male and female, we have to check the normality, and for both male and female, we have to check the linearity. So the first thing is, what we do is we go to the data file and we split the data file into two groups. While splitting data files into two groups, what will happen, that whatever the test will perform, it will divide data into two groups, and that test will be performed on the each group. So what I have done, this you can see that organize output by group. So I have dragged here group which is based on sex or gender. So now whatever the output would come, it would be generating the output by the gender. Okay, so I have already done this first step. I have splitted the data into two. Now in the step number 2, in order to check the linearity, what I have to do is simply I have to go to the scatter plot in the graphs, and I have to plot the data against each other. You know, we have the three dependent variables: total negative effect, total positive effect, and total perceived effect. So we have to compare each variable with rest of the two in order to see that whether the relationship is linear or not. It means that first we'll take the total perceived effect and we'll compare it with the total positive, then we'll compare it with the total negative, right? Then what we'll do, we'll compare the total positive with the total negative. So in this way we are comparing each group of data with the rest of the groups in order to see that it has a linear relationship or not. So how we are going to do this? What's the procedure to plot the scatter plot? Let's move here. I just for you to keep in mind that it simply is a plotting of the graph, not a kind of anything complex. So you can go here, scatter plot. We can go to single scatter plot. In the y-axis, so I told you that first we are going to compare the total perceived with the total positive, right? Then total perceived with total negative, then total positive with the total negative. So first any of the two groups I can take, which maybe for example, I take here total positive and I just compare it with the total negative effect. So it means that these dependent variables should have a linear relationship with each other. Simply click on OK. So this kind of, you know, that the graph, you can just see that the graph for the male is appearing, graph for the female is appearing separately. So this data, I think this was for the total perceived and total negative. I have run for the total negative and total positive, right? So you can just see that the data is making a straight line. It's a downward, something like this. If you just click data here, so there's a kind of a line of data. So it's not a pattern of up down in a way that data is not making a clear pattern of non-linearship. So if we are able to fit a straight line here, and we are able to fit a kind of a straight line here. So data is not making any kind of a cyclical pattern, right? The same way as I have already run for the total perceived against total negative for the male and female. So here you can also see that the data is having an upward trend, so it's showing a straight line. In the case when the data is not making straight line, like let's see what happens that when the data is not linear. I was just checking that if I can. So once the data is not linear, you know what happens, that if this is a kind of a plot, that the linear is this a straight line. If data is not linear, it could have a kind of a this kind of a pattern, right? For example, data would be like something like this. So it's making a kind of inverted U pattern. This is, so you know that this is inverted U pattern, or sometime the data is making a pattern something like this. So it's so it's not exactly a kind of a straight line. So once we say it's a non-linear, this is a non-linear relationship, right? So the linear mean it's going highly up and down, and we don't know that where it's going, what kind of line we can fit to the data. Or another is we say it's exponential. So there is a kind of a growth something like this. So this data is not a linear data, right? So in order to be a data linear, the data should appear in a kind of a straight line, as like kind of this, right? So anyway, we, for the linearity, it's a very complex field, but simply we have to, by looking into the pattern of the data, we have to certain that whether data is linear or not, and then we can move forward. So in our case, the data appears to be linear. The next assumption is this linearity means that there should be a moderate linear correlationship. Then there another term called, the next assumption is multicollinearity. Data should be free from the multicollinearity means that the data should not have a very high correlations. Very high correlations, some of the statisticians and econometricians mention high correlation means more than 0.85, but to be at the safer side, I think we can keep up to 0.80, right? But the correlations higher than 0.85 is considered to be a kind of a dangerous sign. And if two variables have a correlation more than 0.85, so it means that there can be a chances of the multicollinearity. So to check the multicollinearity, simply we go to the our SPSS file, we go to analyze, we go to correlate, bivariate, and is total positive, total negative, total see, all of this test have been just put here. We can just get the Pearson correlation. So put on okay. You see that one thing here, again for the correlations, the data is appearing in the male and female group. So for the correlation, we don't need to get a separate data. So I just go back on the data file, split, and compare groups, and I say that I have just removed that splitting, because for the multicollinearity we have to run all the data together instead of the groups. So now you could just see that for both males and females, the combined data results are coming here. So I have just again moved those results here. We can check, we can find that none of the relationship of the data has more than a value more than 0.80, or maybe in extreme case 0.85. So we can just say that the data is free from the multicollinearity, right? The next there is a assumption is homogeneity of variance. That assumption is tested once we run the one-way multivariate analysis of variance. So this was a very quick demonstration how we can run this one-way MANOVA. If you have any question, you can, since this video is on the YouTube, so you can just give your you can put your question in the comments, so we can answer your question in the comments, right? So thank you very much, and definitely if something is something you feel that should be improved, so you can also give your feedback. Again, thank you very much.